So this is going to be our lecture on the periodic trends. Before you start, please make sure you have your notebook out with your EQs done and you turn to that page with your EQs. It also would be a really good idea for you to have a periodic table out in front of you. One should be available at the front desk. It's like a white periodic table paper. That might be great to write all over, maybe take notes on the actual periodic table. So starting with a little orientation. So the periodic table is organized with things called groups and periods. So whenever I refer to a group, sometimes called a family, but mostly it's group, that is the up and down vertical rows. So this is a group, this is a group, this is a group. Periods are going to be like rows across. So this is a period, okay, straight across, and they are numbered in that manner. So one of the first things you're going to find on a periodic table square like this one is usually the element symbol. A lot of times you're also going to have the element name. Yours does have the element name as well. No need to memorize these. You'll have your periodic table to reference. You'll kind of get to know them the more you use them, but there's no need to memorize them. The other important thing you will find here is the atomic number, which symbol is Z. Usually it's at the top, sometime the middle, sometime the side. And one of the important things about the atomic number is that equals the number of protons. Always, 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 always. Sometimes this equals the number of neutrons and electrons as well, but it always equals the number of protons. It actually identifies the element. And then at the bottom here towards the middle, usually with decimal points, you're going to have the atomic mass, which is the average mass of all the isotopes that exist for this element. Remember, this is not the mass number. The mass number you will not find on the periodic table because that is individual to each atom. And that is the total number of protons and neutrons in that individual atom. You can, however, compare the neutral form mass number with the atomic mass, and it will show you how common the isotopes are for that atom. And I'm going to show you that in a second. So if we look at fluorine here, I can find on the periodic table that fluorine's atomic mass is 18.998. And if I find that fluorine's mass number is 18, I got that neutral form mass number because fluorine's atomic number is 9. 9 plus 9 is 18. I see that these two numbers are really, really close. The neutral mass number and the atomic mass are very close. That tells me that most atoms of fluorine are neutral. It doesn't have a whole lot of isotopes where the mass is really, really different. If you go down here, though, and look at krypton, krypton's atomic mass in the periodic table is 83.80. And it's a mass number for its neutral form. So again, the atomic number is 36. So 36 plus 36 is 72. You can see that these two numbers are a lot more different than the top one, right? So that means that the numbers not necessarily being close indicates there's usually more isotopes than the neutral form of this atom. And again, that's just other pieces of information you can get looking at the periodic table. So the valence electrons, we talked about protons, neutrons, electrons already. A specific type of electron is called a valence electron, and those are the electrons in the outermost orbital, ring, or shell of an atom. So if we look at this atom, it has many total electrons. You can see all the blue dots. But the valence electron is just this one electron on the outermost ring. The reason why we talk a lot about valence electrons is that's the only one really involved in chemical reactions. Because bonding involves movement of electrons, these electrons in the middle here are kind of stuck because they're kind of like surrounded by other electrons. So the only electron that really does anything is the one on the outermost ring, which is the valence electron. So that's why we kind of talk about valence electrons and how important they are. You can easily determine the number of valence electrons using the group an atom is in. So remember, the groups are vertical, and they kind of just go straight across if we look at, I call them the princess towers. So not this middle section. Think like the two, towers of a castle. So this is going to be 1. So every element in this one has 1 valence electron. 2. And you skip over to the other tower. 3, 4, 5, 6, 7, 8. So if any question asks you how many valence electrons something has, you just look to see what group it's in, and it'll tell you how many valence electrons it has. Another thing you could find out using the periodic table is whether an element is a metal, a non-metal, or a metalloid. Okay, so there's going to be this thing called the stair step. It starts at boron and it stair steps down. Anything to the left of the stair step is a metal. Anything to the right is a non-metal. And then some elements, I want to say most, but some that border, meaning touch the stair step, are what we call metalloids. You see there is exceptions here. Aluminum is a metal. Polonium is a metal, okay? But boron, silicon, germanium, those are all metalloids. Now, a metal is not necessarily like iron. A metal just means a certain type of atom. So like sodium, potassium, for example, aren't super, they're not like iron type metal. Non-metal means obviously non-metal, and a metalloid is a mixture of metals and non-metals. That would be the properties. The properties are mixtures. So really just based on this location, where an element is going to tell you whether it's a metal, non-metal, or metalloid. So if we look here, neon is a metal, as non-metal. Zirconium is a metal, right? You just kind of look at what its position is. The periodic table is also divided into different groups, and again, the groups are vertical. There's more than you need to know on this picture, but I just wanted to give you all of them. The big ones you should know is 1A, besides hydrogen, hydrogen's not included in this, are called the alkali metals. 2A are called the alkali earth metals. We skip all the way over the 8A, so this last one is called the noble gases. 7A is called the halogens. And then we get a little, mixed up. For example, these are called the transition metals. Some of these are just called non-metals, but the big ones are going to be 1A, 2A, 7A, and 8A. And we're going to talk about those a little bit further. So one thing you can find with the groups on the periodic table is some common trends. And actually the reason for these trends is because of the similar number of valence electrons. So for example, 1A, that's all the way over to the left, the alkali metals are very, very reactive. They're the most reactive elements on the periodic table. And they tend to form compounds that we call salts. 2A, the second one over, is the alkali earth metals. They are also very reactive, although 1A is a little bit more. We call them alkali earth metals because they're found in the earth. You dig them up out of the ground, and they also make salts. 7A, remember, is kind of on the right side, one in from the right. Those are called halogens. They make a lot of different compounds, including salts, and they're used a lot in everyday life. All the way at the right, the noble gases are very, very unreactive to the point of being non-reactive at all. Some other things, the transition metals in those middle section are very metallic. They're good conductors. They're what you think of when you think of true metals. And then actually the two at the bottom, the two rows at the bottom, are called intertransition metals, and those are all radioactive. So if you look at that list, that's where you have polonium and stuff like that are radioactive. So some trends or kind of common things that you see with the periodic table, other things you can find out of the periodic table are things like the atomic radius, ionization energy of the elements, and electronegativity. So atomic radius, quite simply, is how big an atom is. Ionization energy is the energy you need to remove an electron, so basically how strongly those atoms are holding on to their electrons. And electronegativity is the tendency of an atom to attract an electron, so bring an electron towards itself. You can see here what happens across the rows and down the groups. I'm going to show you this in picture form because I think it's a little bit easier to understand the trends. So if we start with atomic size, again, it goes down across a period, and it goes up down a group. What I think is easier to remember is corners. So the top right corner here is where you find the very smallest elements, and the bottom left is where you find the biggest. And the way that you would compare them is just by their location, right? So if I gave you like lithium, boron, nitrogen, neon, you would just know they go down as you go this way, so lithium would be the biggest. But again, you're going to find the smallest in the upper right and the largest in the bottom left, and that trend follows the whole table. For ionization energy, again, it goes up, left to right, and it goes up, bottom to top. So you find the highest ionization energy in the top right corner and the lowest ionization energy in the bottom right. So it goes up across, and it actually goes down as you go down. But again, I think it's easier to figure out high energy top right corner, low energy bottom left corner. And lucky for us, electronegativity actually follows the same exact trend. So it goes up left to right, so you have the highest electronegativity in the upper right corner and the lowest electronegativity in the bottom left. So it's actually the same trend. And we did go over this in a previous lecture, but I just wanted to kind of confirm. So an ion is where you're going to have a different number of electrons than protons. A cation is a positive ion where you have less electrons. than protons, and an anion is a negative ion where you're going to have more electrons than protons. So where that comes into play this time is with the idea of anion or ion size. So a cation is always going to decrease in size because it's going to be smaller than the neutral atom. So remember, cations are positive because they have less electrons. Less electrons means smaller. So cations will always be smaller than the neutral form. And anions are going to be opposite. They're going to be larger than the neutral form. Again, because you're going to have more electrons, so it's going to be bigger. And then ionic size kind of follows the same as atomic size, where you're going to have, generally the bottom left is the biggest, the top right's the smallest. But remember, the left side is going to, in general, make cations, and the right side, in general, is going to make anions. So that can tell you where you're likely to form the two types of ions. So again, when you take a quiz on this, you will always have your periodic table. It might be a great idea to write some of these trends right on that periodic table, so you kind of always have them in front of you. You always have that in front of you to use on your quiz or test.